Hello, Math 120, and this is Professor Gonzalez, and I would like to go over some problems from homework section 8.3. Now, 8.3 comes from a section called logarithmic functions, and let's go ahead and define that for us. Let's go down here. I cut this out of the book or did a screenshot, and this gives us definition. It says the logarithmic function to the base a, where a is greater than 0. I'm going to highlight that. A is greater than 0, and a cannot equal 1, is denoted by y equals log base a of x. Okay, I'm going to go ahead and do some highlighting here. Let's go to the thing we definitely know, right? Now the base of a logarithm, it's called the base. Well, let me just start by just labeling pieces here. That's called the base. X is called the argument. And y is often called the answer. That just must be because if you want log base a of x, it's equal to this green y, which is the answer of that problem. It's also called the power. And that is because when we convert it from its logarithmic form to its exponential form, this answer right here becomes an exponent, which is the power, right? So let's go ahead and I think what I'm going to do is write it down here. Y equals log base a of x. Now, if this argument is more complicated, we usually put parentheses around it, but that's not needed right now. Now let's go ahead and see how do we convert this to its equivalent form, exponential form, by the way, and it goes both ways. You could go from exponential to log or from log to exponential. And the base of the log is the base of the exponential rather. And so that's the first thing that I start with. And this y value that we called the answer in logarithmic form, remember, is also called the power in its exponential form. And you can put the x on either side. I'm just going to put it here because then it's convenient for me just to show with arrows that the argument just goes right here. Okay. Now, some people will put the x over here, and then so your arrows would do this kind of thing. It would flip-flop, and that's not a bad way to do it, I think, because maybe the brain wants to see it that way. I don't know. But in any case, I always start with the base a, and then I know it's not as easy as the base a and then, whoops, darn it. It's not as easy as the base a and then power x. No, it's the power is going to be the y, the thing all the way on the other side of the equal signs. So you just have to kind of get that down. And let's call this is the logarithmic form called log, and then this is called the exponential form. And those two forms are equivalent to each other, and you can, switch back and forth to whichever form is beneficial to you. And sometimes one is more beneficial than the other. Where we can, it's very nice to switch it to exponential because most people are better in the exponential world because we've done a whole bunch more exponents than we have logs. Okay, so we're going to do this first problem. Let's go up here and go to problem number 1. And there it is right there. So let's go ahead and it just says, please, the logarithmic to the base of a of x denoted y equals log base a of x can be expressed in its exponential form. So here we go. We're just going to do the same thing we're just looking at. And we're going to take its base a, and I'm going to write it as a base a. And then remember, what is it raised to? It's raised to this guy, which is the answer, also known as the power. So there's your y. And then it's all equal to your argument x. And doing that again down here just so it's easier to see. Start with my base raised to y. And, very often people will put the x on the left side because it's solved, but it can go either way. Okay. And then it wants us to make this little statement here. And I actually started recording this and I stopped because it bugged me that a little bit of a typo is happening here with the book, or with at least the online part. See these parts right here? Right? Those parts are just coming from this part of the formula over here, down here. This stuff that I highlighted in green. And that's just saying, right, that a, the base must be greater than 0, and it also cannot equal 1. But notice, so then I went up here and I put it in. A is greater than 0 and cannot equal 1, but they put 1 here. That should be 0. But that's their mistake. So a should be greater than 0 and a cannot equal 1. If you put greater than and then put does not equal in these two places, it gives you a correct answer. All right, let's go ahead. Number 2, change the exponential equation to its equivalent logarithmic equation. Now we're going in the other direction. So let me use my color here. And here's the base. I'm going to zoom in because it's so small. So there's your base, and so I always start with that. That's going to be log base 8 rather. This is equivalent, but it's logarithmic form. And then what's our argument? Let's see. So now we've got 64. And it all equals the exponent. Okay. So 2 equals log base a of 64. Let's do it again here. Like I said, I always like to start. Now this is changing from logarithmic back to the other way, right? Logarithmic to exponent. Okay, let's start off with, I always start with a base of 8. Maybe I'll even do it down below. Raised to what power? It's raised to the second power. And this all equals hardest thing for me is making sure I've got my colors right. So 8 to the second equals 64. And by the way, because it's just an equal, it's an equality, you could write it as 8 to the second equals 64, or 64 equals 8 to the second. They both are the same thing. And once again, you can see my color and what went where. Well, I don't need arrows, do I? I've got the color that's doing it for us. Okay, anyhow, let's do the next one. Change the logarithmic equation to, and then, by the way, this changing from log to exponential or exponential to log is critical and key for being able to do this section. So you definitely have to get that piece down. Helps us understand what's going on too after we kind of get this. So you have to get this sort of muscle memory on how to do this. Like I said, I always like to start with a, the base. So that's going to be a big A for the base. And then that's going to be raised to the third power. And all of that stuff, like I said, you could put that equal sign either way. It's all going to be equal to the argument of 4. Okay, so this is what, number 4? A to the third equals 4, or 4 equals a to the third. Okay, when I do this, I usually, I'm trying to keep my colors and stuff, but I usually, when I do this, I'll just do it this way. I'll say a to the third, and then I'll say that equals 4. But either way works just fine. Okay, now we want to find the value of this exponential, or find the value of this logarithmic expression. Now in the next section, we're going to have properties of logs, which will allow us just to actually look at this and write down the answer. But right now we don't know that. So we want to use our logarithmic definition and translate it to exponential. Now the thing is, we don't have what it's equal to. So what we can do is we could just if we want to know what this expression equals right here, let me use some green. If I want to know what this expression equals, couldn't I just temporarily set it equal to something, and I'm just going to use y, doesn't matter. And if I could figure out what y is, that's what the left side equals, right? So what this does for us is it gives us the three different parts to move around, right? So there's the base, 4, raised to the what power, y, equals 1. So we have 4 raised to the what power equals 1. And you might not know what's going on here, what the answer is, but 4 raised to the y power equals, now you kind of have to, logarithms and exponents, right? They're actually inverses of each other, very closely related. So if I could write 4 to the 0 power equals 1, because 4 to the 0 power is actually in fact 1. Instead of 1, I'm going to write 4 to the 0 power. And now that we've got our bases are the same, guess what? Y equals 0. So the answer to this problem is 0. So log base 4 of 1 equals 0. Let's do another one. I know it's a little weird at first. Once again, when you look at this, you're going to be able to do it quickly because we have a property for it, but right now we don't. So we're going to go ahead and set this equal to y or x or any of your favorite variables. Now we're going to convert this to exponential form. What's the base? 6 raised to what power? Y equals what? 36. Now remember, now you probably can guess the answer. 6 to the what power equals 36. Well, the answer is, isn't it 2? But if we're going to kind of go through some of these motions here, remember, if you can, since this is a base of 6, if I can write this as a base of 6, 6 to the second, then my exponents are equal. And so that's how we did it in the previous section, right? So that shows that. Well, we don't know what that equals, and that's going to be a little bit confusing. So I'm just going to go ahead and set it equal to y. And I'm going to convert it to an exponential. So there's my base of 9. And so it's 9 raised to the y power, and that's going to equal my argument of 1 over 81. Now, once again, how do we solve these exponential equations? Well, we try to have the same base. Now, let's take a note over here. A note over here, 1 over 81. Well, that equals, whoa, what the heck was that? Okay. Don't know what happened. I think anyways, my sleeve or something hit that. So note that 1 over 81 is the same thing as 1 over 9 squared, isn't it? Which is actually equal to 9 to the negative second. So we would prefer to write this as 9 to the negative second. And now you can see the left is 9 to the y. And when the bases are the same, then those exponents are equal. And so there's my answer. Of course, they're asking us to write it in this format using braces. So the answer is negative 2. Okay, we wouldn't want to say y equals negative 2 because it really wasn't a y in the original problem. We just want to say that this whole thing right here equals a negative 2. Okay, next problem, evaluate this. Well, f of 125. So we're going to replace this x with 125. Once again, we've got a great property that will knock this out quickly, but we don't have it yet. That's next section. So we just say, okay, I'm going to set it equal to y, and I'm going to use my knowledge of that I can rewrite this as an exponent. So instead of a log, I'm going to write it, and it's not just an exponent, it's the equivalent exponent to the log, okay? So these are equivalent equations. So this is 5 raised to the y, and that's going to be equal to the argument of 125. Once again, can I write 125 with a base of 5? And yes, I can. 5 raised to the third power is 125. And over here, I've got 5 raised to the y. And when the bases are the same, you can set the exponents equal to each other. And there we go. So what's the answer? The answer is just 3. Okay, so let's zoom out a little bit. Okay, I think I'm going to come back to this in a little bit again. I said that already. Also, something that's interesting to realize, more interesting when we look at inverse functions again, which I'll bring it up. But the domain of this logarithmic function is going to always be, now this as long as you don't shift it, it's always going to be from 0, the interval 0 to infinity, it's open. And then the range is always going to be all reals. Let's do some more problems here. We want to evaluate the function of g of the square root of 2 given this value. Let me get rid of that, get a little more space. So, right, we're going to go ahead and replace this guy with that, right? And so what do we get? We get log base 2 of the square root of 2. Okay, well, this makes you a little nervous, huh? Why don't we set this equal to y and just convert it to an exponential. So what is the base? 2 raised to the y. All of that's going to equal my argument, square root of 2. Now, since logs are inverses closely related to exponents, we always would prefer to write any number, argument, or whatever as an exponent if we can. And you guys remember that square roots, you can think of it a power of 1 there in the index of 2. What is this equal to? Well, this is just equal to 2 to the 1/2, going back a little bit, remember? So the square root of 2 is the same as 2 to the 1/2 power. And remember, on the left-hand side, we had 2 to the y power. And whenever the bases are the same, those exponents are equal, and we're done. So we know now that what's the answer? That's a horrible brace. Try that again. The answer is 1/2. Something that we do want to start remembering a little bit here, and that is going back to this definition, that if we're ever solving, like sometimes you might solve for the base. If you're ever solving for the base a using logarithms, it has to adhere to this whole thing that a is greater right here. A must be greater than 0, and a must be not equal to 1. So a cannot equal 1 and a must be greater than 0. So if you have something that's breaking that rule, a negative a value, or a equals 1, then that would actually be extraneous. Okay. Also we do know that, look at my red argument there. So I've got this x value, and they're saying that those x values, which is the domain, are going to be going from 0 to positive infinity. So essentially we want those x values, the x values must be greater than 0. So that's another kind of clue that when we're solving for the argument, the x value, that we want to make sure that that's greater than 0. And if it's not, we have to reject it. It'd be extraneous. Okay, and we didn't solve for the argument here. We just simplified this whole thing. So that's different. You could have, that's a different situation. All right, let's take a look. And the reason why I said that is because the very next problem, they're actually asking for the domain. So hopefully you understood what I just said. I just said that this argument, right? This argument, I'm gonna highlight it. The argument, whoops, jumping around. The argument must be what? The argument of x plus 7 must be greater than 0. The argument must be greater than 0. So if I solve it, I subtract 7 on both sides, right? And I get x is greater than negative 7. So that is actually my domain. Now, this book is asking us, or at least my math lab is asking us, to please write it in interval notation. So if we write this in interval notation, we would just say, well, it must be greater than, it doesn't say equal to, so it starts at negative 7, open, and must be greater than that, so it goes forever up, which goes to positive infinity. So that is the domain. And that's just another way to say the same thing. Okay, so once again, here we are. It says, please find the domain of the function f of x. And so we look at the argument, knowing that this 7x minus 6 must be greater than 0. So we add 6 to both sides, 7x, add 6 to both sides, divide by 7, and we get x is greater than 6/7. Now that's a great domain. They would like us to write it in an interval notation. So that would just say that x is greater than, so it must be greater than 6/7, and it goes forever up, and it doesn't say equal, it just says greater than, so it is open on both occasions. This is the domain. And zoom out. Okay, next one, find the domain of the function f of x equals log base 3 of, there we go again, this is of the argument, and that argument must be positive, so 3x plus 1 is greater than 0. So it must be positive, but it can't be 1. Let's just make sure it can't be 1, right? It's greater than 0 and it can't be 1. All right, so we subtract 1 on both sides. If I subtract 1, mentally subtract 1 on both sides, get a -1, and divide by 3, and x is greater than, I did not multiply by negative, so it does not reverse the symbol. And so there we go. That is our domain. It should be x is greater than -1/3. So what does that look like? Interval notation, that is just open from -3 to infinity. Once again, that is our domain. Zoom out. It says, graph the function. From the graph, state the domain and range. Well, they're actually having us pick the function. I think I actually want to graph the function so you guys can practice graphing it, and then we'll select the right one. And what I want to do here is, when you get better at logarithms, you're able to just look at them and graph them from just looking at it. But very often, at least in 120 and even further down the line, sometimes looking at a log is just kind of confusing. So remember, so what is the log here? It says f of x equals log base 8 of x. Log base 8 of x. Now the reason why I'm changing it from function notation to just a y is because I want to apply what I learned about changing it from logarithmic to exponential. Let's go through that process again. The base is 8. It's going to be raised to the y power. And all of this equals x. I'm going to put it on this side. All of this equals x. So now the thing that you got to be really careful. Now, see, these two equations will graph the same exact graph. And I think the exponential one's easier to understand because we just know exponents better. But remember, this is solved for x. So when you actually find values, you really want to put in values of y here, right? Because x is already isolated, so you want to put in values of y, which is backwards of what you normally do. But once you remember that, all you have to do is, okay, let me put in value of y. So what if I put in a 0? Whoops, wrong color. What if I put in a 0 for y? What does the x become? Well, it says, well, that's going to be 8 to the 0 power. And we know anything to the 0 power is just 1, unless it's 0. 0 to 0 doesn't work. But anything to the 0 power other than 0 is 1. Let's put something else in there. What if we put in a 1 for this y value right here? So I'm going to put a 1. So it's 8 to the first power, which is just 8. Okay, I'm going to have to sketch this. So I'm not going to be able to do too much more down this line because look at the next one. If I put in a 2 for y, well, looking at my equation up there, that would be 8 to the second power, which is 64. That's a little hard for me to graph on my little graph that I'm going to sketch over here. But you kind of get the idea. And then we can continue. What about, not continue positively, let's go to the negative side. What if I put in a -1? Remember over here, looking at the function, it's 8 raised to the y. So 8 raised to the negative first. And we know 8 to the negative first is just 1/8. So now remember, the thing you got to remember is this is our x value and then the green is our y value. So we can go ahead and graph this, at least make a sketch to try to start it off. I feel like this should move over more, but I guess not. How did I fit this? Let me try again. So looking at my first point, 1, 0. So first point is 1, 0. Second point is 8, 1. 1, 2, 3, 4, 5, 6, 7, 8, 1. The next point is 64, and I'm not going to be able to fit 64 little marks there, so that's not going to happen. But you can see this is a logarithmic curve, which they all look this way. At least the parent, the basic graph does. And it's growing so slowly because I get, that's 1, but I get to 2 where? At 64, 64,2. So it's growing, but it's growing slowly up. Now what happens as I put a negative in for y? Well, you can see right here, I get 1/8. And if that's 1, that's a half, that's a quarter, that's an eighth. It's like an eighth, negative 1. And then if you put in negative 2 for y, you get 1/64. So what ends up happening is this gets closer and closer, but never in fact crosses this vertical asymptotes is what it's called, but it never crosses it. It never touches it. So that is our logarithmic curve, and we're actually able to do it by looking at its exponential form. Okay, and often that's a little bit easier for students to do. Hey, what does that look like, by the way? That looks like A, B, C, or D. It looks like A. Okay, so now the next thing they want to know is what's the domain? Well, what I'm looking at, let me look at mine since it's a little bigger. Remember, the domain is the set of all x values, and this does not get to 0 for x. So it goes from, it doesn't get to 0, so it's open at 0 and goes all the way up here to forever, positive infinity. So the domain is going to be 0 to positive infinity open. And the range clearly goes down, 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 down really fast. So that's going down to negative infinity. And it goes up so slowly, but we have our rest of our life. We just keep on graphing this, which means it just keeps on going up to positive infinity. So the range is all reals. Range is all reals, negative infinity to positive infinity. Okay, let's move on to the next page. Next page, number 14. Number 14, graph the function from the graph, state the domain and range. Okay, same kind of thing. I think with this one, I think we're going to do the same thing, right? Let's take our function over here, call it y equals log base 4 of x. Let's convert that. The base is 4. Can I zoom in? The base is 4. The exponent or power is y. And the whole thing is going to equal x, the argument. Okay, so now this once again gets us maybe to a little more of a comfortable problem to deal with. We've got x and we've got y. I'm going to keep that green just to show that's my exponent. Okay, same procedure as last. And we're going to put in some simple values. How about 0? That was supposed to be green. 0. How about 1? How about 2? Okay, so what is this? I'm going to plug it into this formula, and that was, the base was 4. And so 4 to the 0 is 1. 4 to the 1 is 4. 4 to the second is 16. Let's try some negative numbers. So 4 to the negative first is 1/4. That was a negative 2. That would be 4 to the negative second, which is 1/16. Yikes, that's pretty hard to graph a 16th on this graph. So, but it's always good to just kind of, I mean, you could just look at it and, you know, you could look at it and figure it out from here, which one it is. I think it's kind of nice to practice graphing a little bit. Things start making a little more sense maybe. 1 comma 0 is right here. 4 comma 1. 1, 2, 3, 4 comma 1. 16 comma 2, that's way out there. So this thing is growing slowly, not as slow as the other one. The other one is 64 comma 2. This one's 16 comma 2. And then when we look at negative values of y, we get 1/4 comma -1. So there's -1 right there, but we have a half of fourth. So it's getting close, but not touching. And then of course at -2, it's at a 16th, which is closer, but not touching. This thing gets closer, but never touches that vertical asymptote. Does not touch it, does not cross it. Okay, so that helps us to understand what the heck is the domain. Well, the domain is just going to be, it's going to go from 0 to infinity, and the range is all reals, negative infinity to positive infinity. Pretty sloppy little negative infinity going there. Try again. That's still good enough. And we move on. Oh, we didn't pick which one, right? It's got to be A. All right. Now, change the exponential equations to its equivalent logarithmic form. Okay, we already did this, but we do want to go back over here and maybe do some more definitions, just a couple more here. Let's see. Let's do this. So we've got log base A. Now we have some sort of special logs that happen more often than other logs. So whenever you see, so one log that happens very often is log base 10. And the reason why is because our number system is base 10, and so that really works well with many things. And so, but anyhow, log base 10 is so common that whenever you see log without a base, it's base 10. It's called the common log. Okay, and in fact, it's so common, this is even on the calculator. You'll see a button that just says log. And when you see a button that says log, it means base 10. There's one other log on the calculator, and there's another log that comes up a lot, and that's log base E. And that's so important, it gets its own symbol, ln, which means the natural log. The natural log. Anytime you see ln, it is a log base E. And I think when you're first learning that, it's a good idea to rewrite it as just its full old-fashioned self so you can see the base and know what to do with the base and all that. But once you get used to it, you see ln, you know it's just log base E. It's called the natural log. All right, so that'll help us out with this next step here. And the next step is changing the exponential equation to its equivalent logarithmic equation. Same thing we did before, but now we have an e to deal with. Well, it shouldn't be that much different because e is the base. So now what we have here is log base e. Made that e a little too big. So what we have, and you hear my stomach, I'm starving, I'm hungry. Log base e, and then, so log base e, and then what do we have? Log base e of 12. And the whole thing equals the exponent of the power. Okay, so that's not the way you're going to write it because log base e has its own special notation. What is that notation for log base e? Oh yeah, so the answer is just x equals ln of 12. You don't have to put the e in because it's so special. It gets its own special log name. Okay, now change the logs to the exponential. Well, if we're really new at it, sometimes it's a good idea just to write it as its old-fashioned self, log base e of x equals 12. And this really kind of highlights what's the base. Oh yeah, it's just e. And that's e raised to the 12th power. And the whole thing equals this x. And that's, you're good to go right there. The answer is x equals e to the 12th. Now we'd like to evaluate this function p of x. They would like us to replace e to the 4th with that x value, and they want us to evaluate it. All right, let's do it. So we're going to have the natural log of what goes in there, e to the 4th. Now there's a property that's that we're gonna learn next section that'll be fast, and we know the answer is 4. Okay, and maybe I'll tell you that property just a little bit, just to kind of give you a little prep. But then I'll do it a slow way because we don't know the property yet. But the property basically goes on the idea. Now we know that the ln is log what? Base e. And what's the argument? That's e raised to the 4th. So something that we're going to really start getting into is realizing that a log of a base and an exponent of a base, they're inverses of each other actually. They're inverses. Just like cube root and cubing, right? They undo each other. And so what ends up happening is, and we'll have this written down as a property next, rules or properties of logs. But this log base e and this base e actually undo each other, leaving us with a 4. So that's really pretty quick, isn't it? But we don't have that, sorry. We're going to go ahead and say, okay, figure out what that log is. So if I don't know what it is, I'm just going to set it equal to a variable and try to figure out what y is. And that'll tell me what that stuff on the left is. Well, since I'm not very good at this, I'm going to go ahead and say, okay, log base e of e to the 4th equals y. So now I want to convert this to exponential. Okay, what's the base? The base is e raised to what? Raised to the y equals what? Equals what? Equals this argument e to the 4th. Wait a minute. We found out from maybe section, 8.1, that when the bases are the same, then we can just take the exponent and set them equal to each other. Hey, y equals 4. And that's what I got over there real quick with that inverse idea, which is very handy, by the way. So the answer is going to be p of x equals 4. Okay, now they would like us to find the common log on our calculator. The common log on our calculator. Well, it's just going to be a button that says log. So you punch the log button, you type in 23, it spits out a number. We're going to round it to 4 decimal places. And those 4 decimal places, I'm going to say it's approximately because I'm rounding 1.3617. There we go. Okay, how about natural log? Well, we actually have a natural log button as well. So you're going to look for the button that says ln. And by the way, I just said that these guys are inverse functions. And guess what is above the common log on your calculator, usually written in a different button because you have to hit the shift. You'd have to hit, a shift button to access the blue stuff. Guess what's here? E to the x. I'm sorry. Whoa, what the heck? Where'd that come from? What's the base of this? 10, right? So what's its inverse? Base 10 to the x, or they'll have a caret. What's the inverse of log base, right? Isn't that really log base e? What's its inverse? E. So if you ever want to access e, you have to hit shift in ln because it gives its inverse. If you ever want to get a base 10, shift and hit log base 10 to get its inverse, okay? So the calculator kind of tells you inverse functions. In fact, you can see that with square roots and squares, which is a shaky inverse because they're not one-to-one. But anyways, it does show us inverse functions on the calculator. Okay, let me get back down to this. What I need to do is I need to just punch something because I'm tired. No, punch the button that says ln, type in 6.1, and then hit enter. And what spits out? And this time they only want, wait a minute. They wanted 3 decimal places. Funny book. Okay, last I figured it would be 4, but no, it says 3. So 1.808 just for the heck of it. And so that's what the natural log of 6.1 is approximately, right? We're definitely rounding here. Okay, we're getting there. What's next? Yay, logarithmic equations. Finally, we are going to solve logarithmic equations. Well, do you know how to solve logarithmic equations? Nope, I don't either. No. So the thing is, can't we just change them to exponential, right? Can't we do that? And the answer is yes. Yes. What's the base? 4. Raise to what power? Whoops, and it jumps. 2 equals what? Equals that argument. Equals x plus 3. Well, I like that new equation. It gives me the same exact answer as the old one. I like that much better. I like it much better because all I have to do, this is x plus 3 equals 16, subtract 3 on both sides, and x equals 13. Now I said it gives me the same exact answer as a previous. Well, you got to be a little bit careful because remember we did some domain problems here. X plus 3 better be greater than 0, can't equal 1. So x must be greater than negative 3, right? If I subtract 3 on both sides. Well, 13 is bigger than negative 3, so I'm good. But I just want to put that on your radar that sometimes we can get these extraneous solutions that break that rule that the argument must be greater than 0 and cannot equal 1. In those cases, we'd have to reject if that happens. But we're good here. Let's go ahead and write down the answer of 13. And was there something? Oh, I did want to show another way that I don't see very often. And I like this way a lot because it gets you out of a jam sometimes with logs. So I just want to show you this. This is like, you know, a little bit. It's like to come, and some books don't say it, but when we talk about inverses, so it really belongs in the next section. But I thought I would show it to you. So, what's the inverse of a base 4? Base 4. So if we take the base 4 of both sides, guess what happens here? Guess what happens? Base 4 and log base 4 are inverse of each other and cancel each other out. Guess, look what I have left. I got x plus 3 equals 4 to the second. Isn't that the same thing I have over there on the left by using my rule? Yeah, that's going to give me my same exact answer. X equals 13. Okay, so this inverse idea of undoing it, I like it, right? Why do I like it? Because you guys are used to that kind of thing. Like if someone said x cubed equals 27, what would you do? This is not the problem. This is something different. What would you do? You'd take its inverse, right? You take its inverse and x equals 3. You take its inverse. And so this inverse idea is something we've used a lot with other things. So I think it's a good thing to remember. It's there for us with logs and exponents being inverses of each other. Next problem, let's just stick with what we've got right now. Let's just use the definition of log and take the base of x. So base is x. We're going to raise it to the second power. Whoa. And all of that better equal the argument, 225. Well, here we go. How do you undo a square? You square root, right? So square root, we square the square root, and like I told you, this square root, it does not have a perfect inverse function with it because they're not a one-to-one. So what happens when we square root? We have to say plus or minus, right? Things get weird. So we have to say plus or minus when we square root equation. So we get x equals plus or minus, what's this, 15, right? But we got to be a little bit careful with this because we know with the definition, the base has to be what? Remember, this x is the base that we're looking for. Isn't that the base? It's the base of this logarithm. See, we're trying to solve, now this is my new equation, we're trying to solve, but if you go back to that definition, it said, yeah, you go ahead and write it as an exponential, but the base better be what? The base of a better be, I guess I'll do it in blue. It better be greater than 0, and it better not equal, It better not equal 1. Okay? So why am I saying that right now? Because I just end up getting negative 15, which is not greater than 0. So the negative part has to be rejected, and so the answer is just positive 15, because we're not allowed to have a negative base. Number 22. Oh, there's that old natural log business. You might want to, until you get used to it, just call it log base e, so you know where all the little pieces and parts are going. Now that I see that, I can see, oh, base e raised to the second. That's all going to equal x. Awesome. Okay. And on this particular problem, I erased some of this stuff because it was kind of bulky. I wanted space to work. This particular problem says it wants its exact answer. Okay. So you could put this in the calculator because you do have an E button in the calculator, but it wants the exact answer. So the exact answer is, the exact answer is e to the second. Because once you put it in the calculator, it's an approximate answer. This is called exact. Once you put in the calculator, it's called an approximate answer. Okay. Sometimes they want exact answers. Sometimes they want approximate answers. So you have to look at the directions and look at the input. Okay. Number 23, we're getting there. Number 23 says the natural log of e to the x equals negative 7. Once again, you might want to think about this as log base e, argument is e to the x equals negative 7. Now, if you paid attention to what I said before, and what I said before is, wait, isn't log base e and base e, aren't they inverses of each other? And yep, if you're paying attention, these guys are inverses, leaving us with x equals negative 7. Man, it doesn't get any faster than that. But we're not going to do it that way because we don't have that yet. But I like to give you a preview of some quicker ways to do things that we'll have for us. Now, using the definition and converting this to an exponential is still going to be not the fastest way in this problem, but still essential to know. So let's practice it. What's the base? The base is e. Raised to what power? Negative 7. And that whole thing equals the argument. E to the x, the argument. Wait a minute, aren't the bases the same? If the bases are the same, we know that the exponents are equal, and we get our answer, negative 7, which is the same answer I got over here, but a whole lot faster. All right. Okay, next problem. Solve the logarithmic equation. Well, it's getting a little tougher here. The base is 2, raised to the 5th equals the argument. Okay, so this is x squared minus 17 equals 2 to the 5th is what, 32? And if you add 17 to both sides, we get x squared equals 17 plus 32 is 49. And how do you undo the square? You square root. And when you square root, we say plus or minus. And you remember, be careful. We're saying plus or minus 7. And now, remember before, we had an issue with the problem that had plus or minus. Okay, now this actually is going to be a pain on this one. This one is going to be a pain. I'm not going to lie. To check this, it's a bit of a pain because look what we have to do. We have to take this argument. We've got to say x squared minus 17 better be greater than 0. And so you add 17 on both sides. X squared better be greater than 17. Well, how do we do that problem? Remember how we did this problem way back when? What we did was we said, well, let's get some critical values. What were those critical values? Critical values were found by taking x squared equals 17. So we square root both sides, and we get another mess. Plus or minus square root of 17. And what I'm going to do is I'm going to approximate that just so I have a decimal value to kind of look at. it's plus or minus approximately 4.12. So that allows me to graph it and do our test points. So yeah, this is more than we bargained for. We've got this negative 4.12. The actual exact answer is square root of negative 17, or negative square root of 17. And we've got its positive version over here, 4.12 square root of 17. So this is, it must be greater than, so these guys must be open. And then we just go ahead and run our test points. Let's get a test point right there. How about x equals, what's that, negative 5 would be a great test point in that region. Put in a negative 5 right into that inequality. Negative 5 squared is greater than 17, so 25 is greater than 17. Is that true or false? That's definitely true. So we will shade that part of the graph and say my domain is going to be in this region. So let's continue. So then we go, hey, what about 0? Does 0 work? We put 0 into this, once again, that inequality. So I get 0 squared is greater than 17. Is 0 greater than 17? False. Now we don't have to shade that. How about this last region? X equals, what is that, 5? Yeah, anything bigger than 4.12, 5 would be great. So I have to put 5 into that function. Is 5 squared. Must be greater than 17, and 25 is definitely greater than 17. So that is true. And when it's true, we must shade it. So that's the domain that's allowed. And notice my answers. My answer that I got was plus or minus 7. Well, plus or minus 7, let's see. A negative 7 is like right there, and a positive 7 is like right there. So this is actually okay. Boy, that was a pain, wasn't it? I know you guys think that was a pain. So did I. That's supposed to be a divider line. No, last problem. Okay, find the domain. Oh my goodness. Okay, now find the domain. This is going to be similar to the last one. We want to make sure that the argument, right? We want to make sure that this x plus 7 over x minus 3, we want to make sure that's greater than 0. Okay, well, these are called rational inequalities. They are kind of a pain, but they're a lot like the last problem, where we're going to want to get ourselves a number line in test points, okay? So we need to get our critical values. Critical values. Can't spell all of a sudden. Well, actually, that's not all of a sudden. Anyways, critical values. Critical values, we want to do is we want to figure out what makes the numerator equal to 0. So the numerator, x plus 7 equals 0, that's going to be x equals negative 7. So that's a critical value. And then we also want to know what makes the denominator equal 0, right? So because if the denominator is 0, we've got this undefined situation. So really what makes the denominator equal 0 is something we can't have. Add 3 to both sides, and x cannot equal 3, but that's also a critical value. So we take those critical values and graph them. Now we've got a negative, here's 0. Got a negative 7 right there. Now negative 7 is going to be open, and the reason why it's open is because of the greater than. If it had an equal sign, it would be closed. It does not have an equal sign, so it must be open. And then positive 3 is right about right here. Whoa, that's not good. Positive 3 is about right here. And that also has to be open because x cannot equal positive 3. It will never equal positive 3 because that would make a 0 in the denominator. So that must be open. So there's our critical values. And now all we do is just, it's kind of a long process, but it's, it's the same old process, so it's nothing too new. It's just, figure out a test point. What's a test point in this region? How about negative 8? Well, that sounds good enough. Negative 8. Okay, that's my test point. I'm going to have to put in negative 8 here and here. Now, when I put in, I'm going to go ahead and show it to you, negative 8. But really, we're just looking at signs. Is really, this keeps on sneaking up on me, zooming in. So I put a negative 8 in there, plus 7. and negative 8 minus 3 must be greater than 0. We're really just looking at signs, and the numerator is going to be negative. Denominator is going to be negative. Negative up by negative is positive. Is a positive greater than 0? And that is true. Positive is definitely greater than 0. True. So when it's true, we go ahead and jump for joy and shade it. Dang, this thing is jumpier than something here. Let's see. Keep on. I have not been drinking, so it just can't be me. So anyways, let's take a look at this one right here. And this is x equals 0. So we're going to put in 0 right here and here. And so we actually can see, oh, if you put in 0 there, the numerator is positive, the denominator is negative, and a positive divided by negative is negative. When is a negative greater than 0? Never. So that's false. And we're almost done. Let's try something in this region, like how about 4? Same thing. I'm going to put in that 4 in for x into my inequality. And if I put a 4 in the numerator, I get a positive value. When I put in a 4 in the denominator, I get a positive value. And when is a positive divided by a positive is positive, so is positive greater than 0, and that would be true. So we pull out the purple and jump for joy. And this region is also part of my domain. That's the domain. They'd like us to write it in interval notation. That would be negative infinity up to negative 7 open, union, 3 open, up to positive infinity. And that is called the, right above here, domain. And that'll do it for this one. I hope everybody's doing great, and we will talk to you soon. Take care. Bye.